Moving from the theoretical AI concept, which might need a massive cloud GPU cluster running on, infinite power,
Right.
to a practical real-world implementation on a device that might run on a watch battery for 5 years. Or it needs to process data with absolutely zero latency.
It changes the entire engineering objective, doesn't it?
Completely.
We're no longer just maximizing accuracy towards some theoretical 100% boundary.
Not at all.
We're maximizing efficiency and operational lifespan under, severe constraints: power, latency, memory, and physical security. That's where the algorithmic rubber meets the hardware road.
And that's where the true innovation is happening right now. The core concept here is that moving from centralized cloud processing to local processing, or edge AI, it demands entirely new, non-standard strategies for optimization across every single one of those axes.
So let's start there with that fundamental definition, because the terminology I find can sometimes be a little bit loose.
It can be.
Embedded AI, AI at the edge. What are we actually talking about?
They're basically synonyms for bringing the intelligence, the computation, and the processing capability closer to the data source.
Okay.
We are fundamentally minimizing the reliance on centralized servers and cutting out that round-trip time, that latency penalty to the cloud.
But I have to ask, for the listener who is, used to having massive computational power on tap, why is this movement happening now? If the cloud is infinitely scalable and it's pretty cheap and it can handle petabytes of data, why do we need to put a complex neural network on a tiny chip embedded in a fence post sensor?
That's a great question. It really boils down to 3 factors:
Yeah.
latency, resilience, and data volume.
Okay.
So think about any critical application. If you're building an autonomous vehicle, you cannot afford the hundreds of milliseconds of latency delay.
No way.
Sending pedestrian detection data to a data center miles away and then waiting for the classification response. You just can't. You need local, immediate processing for safety.
And resilience.
Second, right, if you lose network connectivity in a remote location, you need resilience. The device has to still function.
It can't just be a brick.
It can't be brick. And third, many devices generate so much data, think high-definition video feeds, that transmitting all of it to the cloud is just cost prohibitive and wildly inefficient.
So it's better to process locally.
It's far better to process locally and only send back the meaningful metadata or the final insights.
That necessity slams us directly into the core engineering challenge then. These traditional massive ML models, the ones we train on powerful GPUs, they just cannot run on those embedded IoT devices.
Nope. They're too computationally complex, they're way too large for the available memory footprint, and they are, critically, just too power hungry.
Which means the ML engineer's goal fundamentally shifts.
It really does. It's no longer high accuracy at all cost. In fact, you might purposefully sacrifice a fraction of a percent of accuracy to achieve massive gains in efficiency.
So the new goal is?
The new goal is achieving high accuracy with low computational and energy overhead. We have to think small, efficient, minimalist.
And that necessity, that drives specific techniques and hardware architectures. One excellent illustration of this is a case study on energy efficiency cited in the book. It's a real-time people detection embedded system.
Yeah, that was a great one. This successful implementation used tiny ML computer vision, so the amalgamation of ML, embedded systems, and IoT tech on an institutional premise, probably for facility management or security.
And their key to success wasn't just finding the fastest chip, was it?
Not at all. It was smart, integrated systems engineering. They achieved real-time people counting while managing energy consumption brilliantly by integrating solar power into the circuit design. And this is the crucial part, dynamically turning off components when they were not in use.
That sounds simple, but it's actually a very complex challenge for an AI system, right?
It's incredibly complex. The AI model itself has to be intelligent enough to predict when it needs to be active. So if the movement detection model predicts 5 minutes of inactivity, it has to initiate a deep sleep for the whole vision pipeline.
And these kinds of low-level hardware strategies, driven by algorithmic logic, they dramatically increase the device's lifespan.
Which becomes the defining critical metric at the edge. You want the mean time to failure, the MTTF, to be as long as humanly possible.
Right.
Another fantastic example cited involved traffic monitoring systems, a classic smart city application. Researchers Hochsch and Kopetsky optimized complex deep learning algorithms, specifically deep neural networks or DNNs, to run successfully on these incredibly energy-constrained embedded IoT platforms for traffic detection.
And they deployed a powerful toolkit of techniques. Things that any ML engineer trying to slim down a model would recognize. So first, they used model pruning. Can you describe what that looks like in practice for our listeners?
Sure. Model pruning is essentially performing surgery on your neural network to achieve weight reduction.
Yeah.
You identify and remove weights or even entire neurons that don't contribute significantly to the network's output accuracy.
So you're just cutting out the fat.
You are literally cutting out the dead weight.
Mm.
The intuition is that many parameters in a massive DNN are redundant or near zero. So by systematically zeroing them out and retraining a little bit, you can reduce the overall network size, sometimes by 50% or more, with only a marginal loss in precision.
Smaller network, less memory, faster computation.
That's the trifecta.
And crucially, they also relied on quantization, which is maybe the most essential technique when you move away from high-powered data centers and onto, custom ASICs or simple microcontrollers.
Oh, absolutely essential. Quantization reduces the precision of the numerical representation of the weights and the activations.
Okay, what does that mean?
So typically machine learning models are trained using 32-bit floating point arithmetic, FP32. Quantization means moving that down to 16-bit, 8-bit, or even 4-bit integer formats.
And why is that such a massive win?
Because most low-power embedded hardware lacks the dedicated hardware, the high-performance floating point units, to do those FP32 calculations efficiently. Integer arithmetic, like INT8, is significantly faster, it requires drastically less memory bandwidth, and it reduces the memory footprint for storing the model weights.
So this is often the difference between a model fitting on a chip's SRAM or not.
It is often exactly that difference, yes.
So if I understand the trade-off, I'm taking a hit on the precision of my numbers, I'm sort of rounding off some of my weight values, but I gain incredible speed and energy savings because the calculation is happening natively on simpler hardware.
Precisely. And finally, Hodge and Kopetsky used lightweight architecture design itself. This isn't just about compressing an existing network, it's building the network from the ground up to be small and efficient.
How do you do that?
Well, often by minimizing the number of layers, using things like depth-wise separable convolutions, or employing architectures specifically designed for mobile, like mobile nets.
And this optimized model was successfully deployed on low-power embedded platforms, right? It proved its ability to accurately detect traffic conditions with minimal energy usage.
Exactly, making it viable for smart city applications where responsiveness and energy efficiency are absolutely paramount.
So looking ahead, the source material highlights the need for engineers to design for resilience and scalability.
Which moves us into exciting new research directions. We need novel algorithms specifically tailored for edge computing that emphasize resource efficiency, yes, but also scalability and adaptability to dynamic and heterogeneous networks.
And that heterogeneity is key. Help the listener visualize this dynamic network. It's not just one type of sensor talking to a cloud server, is it?
Oh, not at all. The network might consist of ultra-low power environmental sensors, high-powered 5G mobile phones, a local industrial gateway, and even an autonomous drone.
All with different capabilities.
All with vastly different computational capabilities, battery lives, and communication protocols. And the network topology is constantly shifting. An algorithm designed for the edge has to be able to recognize these differences and scale its operations dynamically.
How would it do that?
Well, maybe it sends a complex update only to the high-power gateway while only using a simple binary classification on the smallest sensor node. It has to adapt.
That naturally leads to the concept of distributed systems at the edge. Instead of everything talking vertically to the cloud, the devices start collaborating horizontally.
Absolutely. The future opportunities include sophisticated edge-to-edge communication and collaboration among distributed devices.
They form a mesh.
They essentially form a mesh to enhance data sharing and model training. And this local collaboration reduces the network burden on the central cloud. The source material even notes the integration with emerging technologies like blockchain for secure and transparent data sharing as a future avenue.
To ensure data integrity across these, distrusted local nodes.
Exactly.
So if the engineer you are today understands the theory, the engineer you need to become must master the black art of compression and efficiency. Because the next generation of AI is living in the physical world on tiny amounts of power and memory.
That's the challenge.
Here's where it gets really interesting. Diving into the mathematical mechanics required to operate under these severe constraints. We know our audience is fluent in ML algorithms, so let's examine how the underlying math changes when you're building models for, say, a 16-bit processor instead of a V100 GPU.
Right. We're transitioning from the abstract theory of the algorithm to its precise implementation cost. Because before any complex model runs on that limited embedded processor, data preparation is absolutely crucial.
So the quality, and more importantly, the numerical consistency of the input data that dramatically affects the resources spent.
During both training and inference.
Yes. The book outlines standard mathematical foundations that become non-negotiable at the edge, specifically these basic but essential preprocessing techniques.
Yes, first is normalization, which scales the features into a specific range, usually between 0 and 1.
Okay.
The formula provided is x norm equals x minus x-min divided by x max minus x-min. And then there is standardization, or z-score scaling. Z equals x minus mu divided by sigma.
So why are these simple scaling steps so vital, specifically for embedded AI, compared to a massive cloud setup?
Well, they ensure the features have similar scales. If one feature ranges from 0 to 1,000,000 and another ranges from 0 to 10.
Ah, I see.
The optimization algorithms, especially those that rely on gradient descent, will be overwhelmed by the feature with the massive range.
In a cloud setting, that's just inefficient.
Inefficient, but you can power through it. At the edge, where your optimization algorithms are already heavily pruned and maybe using lower precision math from quantization, numerical consistency is paramount.
So it helps with convergence.
It aids in much quicker convergence during local training and ensures that every step the model takes is efficient without wasting cycles correcting for these massive numerical imbalances.
Let's move to the actual algorithms. Which classic supervised learning algorithms are specifically cited for use in these constrained embedded systems, often for critical tasks like device security or system diagnostics?
Well, the list is selective, focusing purely on models with low inference cost. Logistic regression, or LRC, is frequently mentioned.
Right.
Despite the name, it's a classification algorithm. At its core, it's built around a single perceptron that processes input through a sigmoid activation function, or the softmax function for multi-class classification.
Its simplicity is its strength.
Absolutely. The source provides the form, py1x equals 1 over 1 plus e to the negative x transpose theta. That single exponential calculation is fast, and the model footprint is incredibly small. Simplicity translates directly to speed and energy efficiency at the edge.
But wait, when we talk diagnostics and classification, deep learning usually gets the headline.
True.
Yet we still see the venerable support vector machine, or SVM, playing a huge role here. Why is an algorithm from the early 90s still dominating in some of these embedded contexts?
That's a great question. SVMs are used extensively in classification, and the book cites a really impressive safety-critical example, achieving 98% accuracy in skin cancer detection.
Wow.
And why SVM? Because once the SVM is trained, once that decision boundary and the support vectors are established, the inference cost is incredibly minimal.
So it's very efficient.
It's highly efficient in high-dimensional feature spaces by relying on the kernel trick to map data implicitly into that space. The point is, SVMs can still outperform complex DNNs in some constrained situations, especially when data is scarce or the feature engineering is strong.
And their computational cost during inference is minimal.
Minimal compared to traversing dozens of convolutional layers. The key engineering decision is always on the kernel selection linear, or RBF kernels, and it's often paired with a one versus rest decision function for multi-class problems.
That makes sense. If the model is deployed and not being continuously retrained, inference speed and model size become everything.
Exactly. Now, when deep learning is required for vision, complex prediction, and so on, the building blocks themselves must be chosen for efficiency.
And this is why the rectified linear unit, or ReLU activation function, is mentioned as the foundation of embedded neural networks.
Right, where fx equals max is 0 and x.
This looks computationally trivial. Why is that specific triviality so important?
Because it avoids complexity. Look at older activation functions like sigmoid or hyperbolic tangent. They require computationally expensive exponential calculations.
Right.
ReLU is a simple comparison operation. Is x greater than 0? If yes, keep it. If no, zero it out. This makes it dramatically faster to compute on low-power hardware.
Okay.
So multi-layered perceptrons, or MLPs, then stack layers of these perceptrons using nonlinear functions. And the training procedure relies on backpropagation to adjust weights and bias to minimize the error rate. But that core activation function decision is a huge energy saver.
That discussion of training leads us neatly into addressing a massive constraint: data privacy and volume.
Hmm.
If we can't send all the raw, sensitive data, say patient records or proprietary industrial sensor readings to the cloud for centralized training, we need a smarter method for distributed training.
Enter federated learning.
Right.
This is one of the most critical advances for ethical and resource-constrained AI, especially in sensitive domains like healthcare, where SciPy compliance is absolutely essential.
So what's the core concept?
The core concept is that entities like hospitals, individual phones, or different factory floors share intelligence.
The model updates.
The model updates or parameters, exactly. But without ever sharing the raw, sensitive data, the data stays local, maintaining privacy, while the collective knowledge improves the global model.
How is the network architecture structured to enable this splitting of labor and privacy?
Well, one method discussed is split learning. This is a literal division of the network. It's split into layers.
Okay.
The first layers, often the feature extraction layers, are trained locally on the device, on the client. The intermediate output representations, known as activations, are then sent to a centralized server where the remaining heavier layers are trained.
So only the numerical activations, not the original data, are shared.
Correct. The raw information remains private and on the edge device.
The source also categorizes federated learning based on how the data itself is distributed across clients, which seems like a great way to map real-world organizational constraints to technical architectures.
Precisely. This helps engineers choose the right approach. So let's break down the categories from figure 6.7. If different clients have different features but share data on the same samples,
Okay, give me an example.
imagine two different sensors on the same industrial machine. One measures vibration, the other measures heat. They are observing the same event, the same sample, but have different data types, different features.
Got it.
That's vertical federated learning. It addresses data silos where entities observe the same population but collect different attributes.
Okay, so vertical is about complementary data types on the same event. What about horizontal federated learning,
That's the classic scenario. Clients have the same features but different samples.
like different hospitals?
Exactly. Think of hundreds of different clinics using the exact same diagnostic procedure on thousands of different patient populations. They share the model architecture and the feature schema, but their raw data sets are unique. This is ideal for scaling a model across geographies.
And the most complex version.
That would be federated transfer learning, where both features and samples are different. That requires sophisticated transfer learning techniques to align knowledge between disparate data sets, maximizing the utility of even minor data overlap.
And mathematically, the central piece that holds this collective intelligence together is the update mechanism. This is federated averaging.
This is where the global model is reconciled based on the weighted collective learning of all clients.
Right, and the equation given is fundamental to this. The global version at the next round, GT plus 1, is calculated as a weighted sum of the client models.
The WECA-T, based on the number of samples each client possesses, thunk, divided by the total number of samples, NN.
To distill that equation for our listeners, essentially the smarter clients, the ones with a larger, more comprehensive local data set, represented by N, they have a proportionally greater say in shaping the final global model, right?
Exactly. It's a democratic process weighted by data volume.
It is precisely that. And now we have to transition from the mathematics of training to the true physical economics of deployment. For the engineer focused on embedded systems, understanding system performance metrics is non-negotiable. This is the difference between a proof of concept and a deployable product.
You have to confront the clock, the power, and the packet.
Let's start with network efficiency.
Absolutely. We have to quantify the cost of communication. The round-trip time, or RTT, is simply the measure of responsiveness.
The lag.
It's the lag, the time received minus the time sent. In autonomous systems, minimizing RTT is often the highest priority, and that requires local processing.
And how efficiently are we utilizing the limited connectivity we often have at the edge? That's bandwidth.
Bandwidth estimation, or BW, is defined as the data size divided by the elapsed time. In edge computing, minimizing the data size of the model updates or the inference results,
Through things like quantization.
right, through quantization and efficient encoding, is a direct and necessary way to maximize effective bandwidth.
But the truly defining constraint for any device not plugged into a wall is energy consumption. If your sensor dies in the field due to battery drain, the model's 99% accuracy is entirely worthless.
This is where the systems engineering perspective becomes paramount. We model the total energy consumption, E-total, as the sum of three distinct cost components:
Power.
computation, transmission, and reception. So E total equals E compute plus E transmit plus E receive.
And this decomposition highlights the core trade-offs beautifully. Where do I budget my precious energy?
Exactly. E compute is the CPU power consumption times the CPU computation time. E transmit is transmission power times transmission time, and so on.
Right.
The fascinating engineering decision is, do you spend more CPU energy processing a large file locally, which increases your computation time but greatly reduces your transmission energy? Or do you compress the model update so much that it risks accuracy but saves a massive amount of transmission time?
So optimization techniques like pruning and quantization are designed to reduce both at the same time.
To reduce computation time and transmission time simultaneously.
Yes, it's a constant battle of minutes versus milliwatts. Then we have quality of service.
Right. We measure service response time, or SRT, which is crucial in real-time applications. TSRT is the sum of processing time, queue time, so waiting for the network or hardware resources, and transmission time.
And minimizing that queue time often requires clever OS design or hardware prioritization.
It does. And finally, reliability and fault tolerance, which is just mandatory for any deployed embedded system, especially in industrial or medical contexts.
Okay.
We measure system availability, A, using the mean time to failure, MTTF, and mean time to repair, MTTR. So A equals MTTF divided by MTTF plus MTTR.
And in embedded systems, the focus is heavily on increasing that MTTF, extending the operational lifespan.
And as we noted earlier, AI models themselves are now being used to predict node lifespans and resource depletion, allowing systems to proactively manage their resources to maximize this MTTF.
Now we get to see these intricate constraints and mechanics in action. And we can start with arguably the most resource-constrained and widespread deployed environment: wireless sensor networks, or WSNs.
Yes.
The problem here is almost always defined by energy, and the distribution of that energy.
WSNs are the very definition of low power. They're typically distributed and often running on finite, irreplaceable batteries in remote locations. The need for AI in these networks is driven by the fact that many real-world WSNs are heterogeneous networks.
Meaning the nodes have different energy levels.
Exactly. For efficiency or cost reasons, the nodes often have different initial energy levels, categorized in the research as normal, advanced, super, and even ultra nodes.
And traditional routing and clustering protocols, they struggle dramatically with this uneven playing field, right?
They do.
If a basic protocol treats all nodes the same, the high-energy ultra nodes get underutilized, or the low-energy normal nodes die first, killing the network segment way too soon.
Exactly. They lack the sophistication to adapt to that resource disparity. That's why AI and ML are so essential.
So they optimize energy use.
By predicting network conditions, designing better routing protocols, and dynamically adjusting sensor sleep-wake cycles based on predicted traffic. A specific protocol mentioned in the source material, which is optimized for heterogeneity, is the EDCH protocol and its 4-level enhancement.
And the EDC4 level protocol, that heightened the level of heterogeneity by introducing those ultra nodes, right? Which possess even higher energy reserves than the supernodes.
Correct.
So explain the key metric they track and why the AI is so successful at improving it.
The key metric is the stability period. This is defined as the time, measured in operational rounds, until the very first sensor node in the entire network dies.
Okay, that makes sense.
Once the first node fails, the network's reliability is compromised. The goal is to keep every single node alive for as long as possible. And the source material provides compelling data showing that the EDC4 level protocol, because of its AI-driven logic, significantly extends this stability period.
And these numbers are not trivial. We're talking about massive gains in operational lifespan.
Oh, they are massive.
Yeah.
For instance, in a simulation of a 100-node network, the existing technique achieved 964 communication rounds before the first node died,
Okay.
while the proposed AI-enhanced EDC4 technique reached 1,462 rounds.
Wow. That's an increase of over 50% in operational lifetime before system failure.
Just by applying smarter resource management.
And that smart management isn't just about longevity, it's also about smarter allocation of the workload.
Absolutely. The AI-driven metric improvements cited in Chapter 11 show that the AI models predict sensor node lifespans to extend that stability period.
Right.
Furthermore, adaptive clustering algorithms are employed to reduce unnecessary transmissions, which minimizes energy dissipation. That's a critical component in that E-total equation we discussed earlier.
So if a sensor knows a nearby node is reporting similar data, it can just stay asleep. So the cluster head selection process, who gets the job of processing and relaying data, is now far more sophisticated than simply choosing the nearest node or the one with the most remaining power.
Precisely. AI-powered cluster head selection considers not just remaining energy, but also factors like processing power, the sensor's current workload, its spatial proximity to the base station, and its real-time predicted traffic volume.
So it's a multi-factor optimization.
Right, and this maximizes the data packets collected at the head node, ensuring that the network operates efficiently both in terms of power and data utility.
Moving from the large rural sensor network to the most contained and constrained environment of all the human body.
Hmm.
We find the revolution of healthcare happening from the inside out using augmented reality and edge AI.
We're talking about ingestible sensors, or smart pills. These are miniaturized, biocompatible electronic devices that measure vital physiological parameters as they navigate the GI tract.
So things like temperature, pressure, pH.
Temperature, pressure, pH, and even chemical composition, looking for biomarkers of disease. And they transmit this data wirelessly, usually via body area networks or to a device worn externally.
And the integration with augmented reality, or AR, that provides the visualization layer.
It does. AR overlays this digital information, the live sensor data, onto the real world. You are taking abstract data and tying it physically to the patient's anatomy.
So the proposed systems envision physicians virtually navigating the GI tract.
During a virtual colonoscopy, receiving live, actionable data overlays on inflammation, lesions, or abnormalities detected by the smart pill. This is critical for early diagnosis and minimizing invasive procedures.
But this is the critical juncture where edge computing becomes a non-negotiable necessity. If the pill is moving through the digestive system, the analysis has to be instant.
Correct. That data temperature spikes, pH changes, early signs of inflammation, it must be analyzed at the edge. If you are monitoring a developing abnormality, you need real-time, low-latency analysis to potentially enable personalized interventions.
Like automatic medication release.
Or a critical alert to the physician. Centralized servers introduce an unacceptable delay. If the latency is even a couple of seconds, the smart pill has already moved significantly down the GI tract, making precise anatomical localization and immediate intervention impossible.
So local processing on the user's device or a nearby external node is the only way.
It's the only way to meet that low latency requirement for critical diagnostics.
So Edge AI isn't just about saving energy in a remote warehouse. It's about saving time and lives by delivering immediate actionable insights exactly where the data originates.
Now let's look at another area where speed is paramount, but the data volume is staggering. Object detection and real-time vision. This is central to embedded systems like autonomous vehicles and advanced robotics.
We know that computer vision, particularly deep learning for detection, requires enormous computational resources. So how do engineers fit a system that processes gigabytes of image data per second onto these resource-constrained embedded platforms?
Well, the initial framework relies on tools like OpenCV, the open-source computer vision library, in Python for robust image preprocessing. But the real optimization comes from using specialized deep learning models that are tailored for speed over absolute accuracy.
These are the state-of-the-art models famous for single-pass analysis.
Exactly. We rely heavily on models like YOLO, which stands for You Only Look Once.
Right.
It's known for its speed because it predicts bounding boxes and class probabilities simultaneously in a single forward pass, unlike older methods that required multiple stages. We also use optimized versions of faster RCNN and SSD, the single-shot multi-box detector.
Can you quickly delineate the trade-off between those three for our audience?
Certainly. Older models like RCNN were highly accurate, but way too slow for real time. YOLO sacrifices a tiny bit of precision for phenomenal speed, making it the preferred choice for truly embedded, rapid systems where latency is everything.
Like recognizing a pedestrian crossing the road.
Exactly. SSD offers a middle ground, often balancing better precision than YOLO while maintaining a highly efficient architecture by predicting bounding boxes at various scales.
So an ML engineer at the edge has to carefully weigh that 2 or 3% drop in accuracy from a highly pruned YOLO model against the guaranteed millisecond processing time.
That is the daily trade-off, yes.
Yeah, and the applications are ubiquitous, driving massive changes in industry and consumer life.
In autonomous driving systems, these models must recognize pedestrians, vehicles, and traffic signs in that critical 50 to 100 millisecond window.
Right.
In retail, they power applications like Amazon Go, where cameras and sensors detect products picked by customers, eliminating the need for traditional checkout.
By analyzing every shopper's actions locally.
And they also enable sophisticated augmented reality applications, overlaying maintenance instructions or diagnostics directly onto physical objects in real time, which greatly enhances industrial efficiency.
These case studies just underscore the recurring theme. The ML engineers specializing in embedded systems must prioritize the low-level mechanical efficiency of the algorithm, the CPU time, and the transmission time savings, as much as the high-level accuracy score.
Absolutely.
Transitioning from efficiency to resilience and trust, we have to address the sophisticated security challenges that plague embedded systems once they are deployed at the edge. Unlike heavily secured centralized server farms, these devices are often physically accessible, which leads to entirely new classes of attacks.
It does. This introduces physical threats that ML engineers rarely think about during initial training, specifically side-channel attacks, or SEA, and hardware trojans, or HTs.
Okay, let's define these vividly. What's a side-channel attack?
A side-channel attack is akin to listening to the electronic chatter of a chip. It exploits physical emanations from the device, things like instantaneous power consumption patterns, electromagnetic leaks, or precise timing variations to extract secret information.
Like cryptographic keys.
Often cryptographic keys or proprietary model weights. An attacker analyzes the power signature of a chip executing an encryption algorithm to deduce the key bits being processed. It's electronic eavesdropping.
And hardware trojans are the ultimate sleeper agents.
They are. They are malicious, tiny modifications built into the silicon chip design itself, often inserted by an untrusted third party during the complex manufacturing supply chain.
And they're incredibly stealthy.
Incredibly, they're often inactive during testing. A Trojan might simply wait for a specific environmental condition, a high temperature, or a specific input sequence before it activates to exfiltrate data or cause a system failure.
What's fascinating is that machine learning models are now being employed as the defense mechanism against these physical threats.
Exactly. ML models can be used to analyze that electromagnetic emanation data gathered from an active chip to detect the presence of stealthy hardware Trojans.
So it learns what's normal.
The defense model is trained on what constitutes a normal physical signature for the device during operation. When a Trojan, even an inactive one, slightly alters the capacitance or the power draw, the ML defense model flags the anomaly. It's like an advanced physical signature analyst.
So let's look at the hardware and software countermeasures integrated into these SCA-resistant embedded systems. These are now crucial elements of the architecture design process.
Right. Proactive engineering solutions are mandatory to obscure the side channels. At the hardware level, techniques include dynamic voltage scaling and noise injection.
So what does that do?
By constantly and randomly fluctuating the chip's operating voltage or injecting random noise into the power line, engineers obscure the clear power consumption patterns, making those power analysis attacks much more difficult.
This is literally scrambling the signal the attacker is trying to listen to. What about timing analysis?
For timing attacks, they use random jitter clock generation. This introduces deliberate, randomized variability in the clock signal, which prevents an attacker from timing sensitive operations accurately.
So if the clock speed is constantly changing,
The attacker can't precisely link a specific energy spike to a specific instruction in the cryptographic algorithm.
and what are the software and algorithmic defenses?
They rely on secure execution modes, which use cryptographic random masks to obscure intermediate values during sensitive computations.
So it reduces leakage.
It reduces data-dependent leakage. You protect sensitive data even while it's being processed in the cache or registers. The system also integrates sensor-based anomaly detection, where physical sensors monitor environmental conditions like heat, unusual vibration, or physical tampering, and trigger countermeasures or shut down the system if readings exceed predetermined thresholds.
The book even provides a conceptual algorithm for this sensor-based defense. It's a simple, robust logic protecting complex secrets.
It is, but this complex security architecture introduces the inevitable engineering trade-off. The source material highlights this with very clear data. System performance, meaning speed and throughput, demonstrably decreases as the security level increases.
So as you combine these masking and noise and checking techniques,
Your performance goes down. Adding noise, masking data, and checking sensors all take precious time and energy, directly impacting those critical metrics like RTT and eTotal.
you buy security with a loss of speed?
That is the ultimate budget decision the deployed engineer has to make.
Moving from technical security to ethical resilience, we have to consider the risk of algorithmic bias once these embedded systems start making real-world decisions in safety-critical applications like clinical diagnostics or autonomous controls.
Mm.
Transparency and accountability become paramount for public trust.
And the source cites a deeply concerning case study from healthcare, where a clinical algorithm, which was widely adopted by hospital systems, exhibited significant racial bias.
And this is a vital example because the math of the algorithm was fine. The problem lay entirely in the training data.
Exactly. The model was trained on historical healthcare expenditure data, not just symptoms. And because of systemic economic disparities, the data reflected that certain demographic groups had lower historical spending on healthcare.
And the model learned to equate lower historical spending with lower disease severity, regardless of the current symptom.
Precisely. As a result, Black patients had to exhibit significantly more severe acute symptoms than white patients to trigger the same level of recommended care or intervention from the algorithm.
Wow.
The algorithm simply encoded and amplified an existing societal bias. It's a demonstration of how historical data reflecting inequality can translate into dangerous algorithmic disparity in deployment.
The lesson there is clear. The embedded engineer is not just writing code. They are responsible for the societal footprint of the training data. What solutions does the book outline for engineers to mitigate this ethical challenge once the model is trained?
Well, these include bias detection and mitigation techniques. Things like reweighting training examples to give underrepresented samples more influence, or modifying decision thresholds manually to ensure fairness across demographic subgroups.
Okay.
They also discuss counterfactual fairness, which involves assessing whether the system's outcome, for example, a diagnostic recommendation, would change if a person's sensitive characteristic, like race or gender, were hypothetically varied, keeping all other factors constant.
And finally, protecting the underlying raw data, a fundamental privacy requirement for any embedded ML system, requires two core cryptographic techniques that we need to understand.
The first is differential privacy, or DP. The core idea is that you add calculated random perturbations, noise to query responses or dataset elements before sharing them,
And that safeguards individual privacy.
by ensuring that the inclusion or exclusion of a single individual doesn't significantly impact the output of the query or model. You can learn about the group without revealing anything about the person.
And the second is frankly astounding from a cryptographic perspective. Homomorphic encryption, or HE.
It's amazing. Homomorphic encryption allows computations to be performed directly on data that remains fully encrypted, without ever decrypting it first.
So you're working inside a locked box.
Imagine giving a computation engine a locked box of numbers, and it performs addition or multiplication inside the box and hands you the resulting locked box. Only the intended recipient with the key can see the final computed result. It's the ultimate tool for preserving data confidentiality.
Before we wrap up, we need to quickly address the rise of automated deep learning, or ADL. This technology simplifies model creation, which sounds great for democratization, but it comes with a strong engineering warning that the source material emphasizes.
Right. ADL automates the ML pipeline systems like neural architecture. Search, autonomously find the best performing network structure to enable people, maybe clinical researchers or domain experts with little specific coding knowledge, to produce DL algorithms.
Which is very powerful.
Immensely powerful. However, the engineering warning is that researchers must still be profoundly cognizant of ML best practices.
Such as preventing basic errors that ADL might obscure.
Exactly. You must ensure sufficient label distribution and, critically, prevent data leakage between training and validation sets, even if the architecture was generated automatically.
And the most non-negotiable step.
Rigorous external validation. Even if ADL simplifies training on cloud GPUs, the resulting models must be tested extensively on regional populations, or populations different from the initial training pool, before deployment.
So a model trained on patients in a metropolitan American hospital might not perform effectively on a different genetic or regional population.
Exactly. This continuous performance evaluation is essential for reliable and safe AI.
That was a tremendous deep dive into the algorithmic edge. And it illustrates that the shift from cloud AI to embedded AI is not just a migration of code, but a complete transformation of engineering priorities.
It means the battlefield has changed. The successful ML engineer operating in the embedded space is no longer solely judged by their F1 score.
Right.
They are masters of system optimization, power efficiency, latency reduction, memory footprint management, and ensuring ethical resilience against bias and security threats. The challenge is achieving complexity under severe hardware and energy constraints.
We've seen that the future of AI is not centralized only in the cloud. It's decentralized and distributed, living in the physical world on microdevices.
And this demands that ML algorithms become lightweight, resilient, inherently secure, and trustworthy.
So you must be equally comfortable with the federated averaging equation as you are with the total equation.
The pressure on the software side is immense because the hardware capabilities are so rigid. Techniques like quantization, pruning, designing for heterogeneous networks, and implementing side-channel countermeasures are no longer optional best practices.
It's core requirements.
There are core requirements for system deployment and operational longevity.
So we leave you with one final provocative thought to mull over as you design your next model for the edge. We discussed how advancing research in explainable AI, or XAI, and model interpretability is essential for building public trust, particularly in safety-critical applications like advanced diagnostics and autonomous systems. Given the increasing deployment of AI in these crucial, life-affecting areas where a failure can be catastrophic, how far away are we from regulatory systems mandating XAI and continuous performance evaluation for every single embedded AI model deployed in the field?
It's a question of trust, ethics, and liability that the entire industry has to answer, and probably very soon.